different, but for our purposes, they're going to be the same. These values, osmolarity or osmolality, reflect the concentration of particles within plasma. If osmolality or osmolarity is up or serum sodium concentration is high, that increased concentration of solute is going to be sensed by osmoreceptors present within the hypothalamus. You know, the hypothalamus has an intimate relationship with the pituitary. They're connected by that pituitary stalk. So the pituitary hangs off of the hypothalamus. Well, when these osmoreceptors are stimulated, it's going to trigger release of ADH from the posterior pituitary. That ADH is going to be released into the bloodstream. It's going to bind to receptors within the late DCT and collecting duct, and it's going to trigger insertion of these aquaporins, which allows for more water to be reabsorbed. So that 25% of the filtered water that has yet to be reabsorbed in the presence of elevated levels of ADH, most of it gets reabsorbed. Okay? And of course, what that does is, as it's reabsorbed back into the bloodstream, osmolarity falls and plasma volume increases. Now, the second trigger is a drop in blood pressure or plasma volume. You see there are baroreceptors or stretch receptors in the atrium, particularly the right atrium, and also in some of the larger veins emptying into the heart. When these stretch receptors sense a decrease in volume, a decrease in stretch, there's less blood returning to the heart, they trigger release of ADH from the posterior pituitary. So that what happens? We hold on to water and our volume increases. So in that way, we can raise blood pressure. Now, at the same time, it results in a smaller volume, more concentrated urine. Okay. This is what happens if ADH levels are low. ADH levels are low. If we've been trying to drink a lot of water, we're trying to, for instance, let's suppose a lot of people drink at least 8 glasses of water when they're trying to lose weight. You know that? You hear that? People drink, and a lot of people think good hydration is healthy. So if your volume repleted, meaning that you have plenty of volume, you have plenty of water, then ADH levels are going to be relatively low. So that when the filtrate returns to the DCT and collecting duct, okay, remember that as it reapproaches the cortex, its osmolarity is going to be less than it was in the PCT because of those events that are occurring in the ascending limb. Well, so its osmolarity, instead of being 300, it's only 100. Now, without ADH, look, there are no aquaporins here, or very few, to allow any further reabsorption of water. There's some, so there's a slight drop, but not much, not much. We tend to instead hold on to water as that filtrate moves through the late DCT and collecting duct. And so that the sum total effect is that as filtrate is moving through, it actually becomes a little bit more dilute. And we produce a very dilute urine in the absence of ADH. Okay? And the reason ADH is not being produced is because we're already, you know, our osmolarity is already normal, our vascular container is full. Now let's look what happens though if ADH levels are high. Okay? Here we have the filtrate, again, reapproaching the cortex. Its osmolarity is about 100. That's what we see right here. Its osmolarity is around 100. Okay? Now, what we have here. We previously established this medullary osmotic gradient. This medullary osmotic gradient was established by juxtamedullary nephrons. The renal tubules of which descended all the way down toward the papilla. Remember that as the filtrate was passing through these juxtamedullary tubules, as it moved up the ascending limb, solute was being dumped into the interstitium. Of course, there was more solute available deeper in the medulla than there was higher up. Okay? Water was left behind. And so the filtrate itself was becoming more dilute as we moved upward. Okay? Whereas at the same time, we were creating this osmotic gradient, where there was a 200 milliosmol difference in concentration of solutes between the interstitium and the renal tubule at any one level. And at the same time, we created this gradient from cortex to medulla. Okay? Well, this gradient is going to be important in terms of the ability to concentrate urine. As this relatively dilute filtrate comes up into the DCT with an osmolarity of 100, if aquaporins are present, then water is going to be able to follow an osmotic gradient. In other words, if the filtrate osmolarity is 100 here within the renal tubule, and it's 200 here within the interstitium, and there are aquaporins present, what is water going to do? It's going to move into the area where the osmolar concentration is higher. The number of solutes is higher. Okay? So as it's rounding this bend from the DCT into the collecting duct, water is moving out. Okay? And it's going to keep moving out until look what happens here. Now, at this segment here, we have equilibrium. The filtrate osmolarity as a result of the movement of water is equal to the osmolarity within the interstitium. But then as the filtrate moves down, look, we come across another gradient. Okay? As long as aquaporins are present, more water is going to exit. And so what happens here? We achieve an equilibrium. Well, that equilibrium is not going to last long because as we move down the collecting duct, the interstitium becomes more heavily concentrated with solutes. So as we move down more, we encounter another gradient, where water then leaves the collecting duct and moves out into the interstitium. Again, it establishes an equilibrium for a little bit until we come down further within the tubule. And so this process keeps occurring again and again. Water keeps leaving as long as the medullary osmotic gradient keeps increasing. So you're going to see what happens as water moves down the collecting duct, as filtrate moves down the collecting duct, I should say, it becomes increasingly concentrated. So that very little water is available at the renal papilla to be excreted as urine. We produce a smaller volume, more concentrated urine as a result.
You said as the medullary increases?
The medullary osmotic gradient. That's this increase from 300 to 400 to 600 to 800 to 1,000. Okay. This medullary osmotic gradient was established by juxtamedullary nephrons. It was established because in the ascending limb, we're dumping solute. And more solute is dumped in the deeper part of the medulla than is available to be dumped or transported up near the cortex. So when we first talked about the difference between juxtamedullary and cortical nephrons, we said that although juxtamedullary nephrons only account for 15% of your nephrons, they're responsible for the concentrating ability of the kidney, because they're the ones that establish this medullary osmotic gradient that's capable of pulling water out of the DCT and collecting duct. Okay?
So this is what happens under normal circumstances.
Well, to some degree, it depends upon if you're dehydrated. That's what would happen. It depends upon your level of hydration and your blood pressure.
Okay.
Okay? If you're dehydrated, yeah, we're going to hold on to most of our filtrate. If you're not dehydrated, then you're going to produce less ADH. So you're going to hold on to some, of the water within the filtrate, but then you're going to produce a clearer urine because your urine's going to be a little bit more dilute. So on average, we only excrete about 1% of the filtrate we form. The other day we said that if you look at the GFR, the amount of filtrate formed per minute, and you multiply that times the number of minutes per day, that over the course of a day we produce 180 liters of filtrate. Okay? Normally, we reabsorb 99% of that, which means only 1% of the filtrate of the salt and water, if you want, gets excreted. Well, 1% is about 1.8 liters. That's probably about an average amount of urine per day. If you're dehydrated, do you produce 1.5 liters? No, because in the face of dehydration, okay, you're holding on to salt water. So it's going to be less. Yes?
No, okay, this might be a crazy question, but that 1% of filtrate that we excrete, if we drink more water, will we excrete less?
Oh no, if you drink more water, you'll produce less ADH, and you'll excrete more water. So if you're drinking water all day long, you're going to be peeing more,
Okay.
because you're inhibiting release of ADH. Okay, as you absorb more water into your bloodstream, what happens to serum osmolarity?
Or
It
decreases.
decreases,
Yeah.
and that inhibits release of ADH. It's increased osmolarity that triggers its release. So let's talk about our friend Al. We said ADH is responsible for what happens to the remaining water that reaches the DCT and collecting duct. Whereas our friend aldosterone, not albumin. Aldosterone is responsible for what happens to the remaining salt. Okay? Now, you know that the major stimulus for release of aldosterone is the renin-angiotensin pathway. Okay? And so those triggers that stimulate the renin-angiotensin pathway are the same triggers that stimulate release of aldosterone. They go hand in hand. So low blood volume, low blood pressure, sympathetic stimulation, the things we think about for renin-angiotensin, okay, those are the triggers also for aldosterone. Now, there are a couple of other triggers for aldosterone. High potassium levels within the blood. That's called hyperkalemia. That will directly stimulate release of aldosterone from the adrenal cortex. Why? Well, hyperkalemia is a life-threatening electrolyte abnormality. It can result if potassium levels climb too high, it can result in cardiac arrest. So as potassium levels begin to climb, they trigger release of aldosterone. And remember, aldosterone, what it does at the level of the renal tubule and collecting duct is it stimulates pump activity, where we reabsorb sodium in exchange for secretion of potassium. So it makes sense that high potassium levels would trigger release of aldosterone, which in turn causes the kidney to excrete potassium, so we can get rid of it. Now, a third stimulus that we'll see in the next diagram is that low levels of sodium, hyponatremia. So not hyper, but hypo, H-Y-P-O, can directly stimulate aldosterone release. That makes sense because aldosterone then is going to tell the kidneys hold on to salt, to sodium, reabsorb it in exchange for secretion of potassium. So these are some stimuli for aldosterone release. Aldosterone is going to regulate the final amount of sodium that gets excreted or reabsorbed. We look at it either way. So remember that as the filtrate approaches the DCT and collecting duct, 90% of the sodium has already been reabsorbed. God bless. What happens to the remaining, the residual 10%, depends upon the level of aldosterone. if aldosterone levels are high, most of that residual salt gets reabsorbed. All right? And that makes sense, by the way. Those stimuli, many of those stimuli for release of aldosterone are the same stimuli for release of ADH. In other words, low blood volume, low blood pressure. Those stimuli trigger release of ADH, but they also trigger the renin-angiotensin pathway. Okay? So that if we're going to reabsorb more sodium in the DCT collecting duct, water is going to be free to follow. Why? Because aquaporins are going to be inserted. And so in the face of low blood pressure and low blood volume, we're holding on to salt, and water is going to be free to follow. And that additional salt in water that's being reabsorbed is going to be dumped into the bloodstream. So that we're going to increase blood volume. We're going to raise blood pressure. Okay? Now, how does aldosterone work? Okay? It triggers placement of those sodium-potassium pumps in the DCT and collecting duct. Remember, these are sodium-potassium ATPase pumps, meaning that they're active transport pumps. They require energy. Okay? So all along, we place these pumps along the basolateral membrane, okay, that cause reabsorption of salt, 3 sodiums, remember, in exchange for secretion of potassium, 2 potassiums. So all along here, we're placing these pumps. Reabsorb salt in exchange for secretion of potassium. So, in the absence of aldosterone, then we don't have many of these pumps to reabsorb salt in the late DCT and collecting duct. But in the presence of aldosterone, we're inserting new pumps so we can reabsorb more salt. So high levels of aldosterone lead to increased sodium reabsorption and potassium secretion.